Hello everyone, my name is Iñigo Capellán-Pérez, and after the session 5.1 on the human interference in the climate system and climate modeling in MEDEAS, I will present the session 5.2 of the course, which is focused on the modeling of climate change damages in the model. As acknowledged in the Paris Agreement, climate change represents an urgent and potentially irreversible threat to human societies and the planet. The modeling of climate change damages to human societies is a very challenging topic given the complex uncertainties that pervade the coupled human-Earth system, the long time horizon of the problem, as well as the heterogeneous nature of climate impacts across regions, sectors, and generations. Hence, large uncertainties exist for its assessment. Global surface temperature has already increased around 1 Celsius over pre-industrial levels, and climate change impacts are already affecting human societies. What is clear is that natural disasters negatively affect the development of a country, causing a lag even after the recovery phase due to a combination of direct and indirect impacts. For example, intensification of extreme weather events such as cyclones, heat and cold waves, provoking forest fires, drought episodes, etc., which together with long-run climate change critically damage biosphere dimensions such as the water cycle and biodiversity. These impacts may make large regions unlivable, raise mortality, and trigger large-scale migrations across the globe, cause loss of economic production, destroy goods, capital, and infrastructure. In fact, adaptation to climate change is generally expected to only play a limited role. In this context, political accords such as the Paris Agreement have set the objective to avoid global average temperature increase to be well below 2 degrees and pursue efforts to limit the temperature increase to 1.5 degrees. Now, let's see how models address all these issues. A review of the literature shows that there is a large gap between natural scientists' understanding of climate change impacts and the representation in integrated assessment models. For example, Hansen and colleagues studied paleoclimate data, climate modeling, and modern observations, concluding that 2 degrees of global warming above the pre-industrial level would be dangerous. Knutti and colleagues also showed that the common target of 2 degrees is a political target, not having been explicitly recommended by any scientific assessment as a safe target. One more example, the recently updated reasons for concern figure from the IPCC special report on 1.5 degrees shows that there are from moderate to high impacts and risks for people, economies, and ecosystems across sectors and regions associated to this temperature increase level. However, in integrated assessment models, temperature change typically increases in business as usual scenarios between almost 4 and 5 degrees by the end of the century, with negligible representation of impacts and damages to humans at the biosphere. Thus, the potentially irreversible threat to human societies and the planet stated in the Paris Agreement is not currently being captured by models. This discrepancy inevitably produces confusion in policymakers and the citizens as they receive contradictory messages from the scientific community in relation to the potential damages caused by climate change. In this context, MEDEAS proposed a novel, simple, and transparent methodology based on the concept of damage function in order to introduce climate damages into the modeling framework. Damage functions consider climate change impacts as highly aggregated monetary damages. Although neglecting non-market impacts such as ecosystem functioning, conflict, illness, etc. is a shortcoming, this approach allows to calibrate the damage function through top-down induction consistently with climate change impact assessments. The literature shows us two main lessons. First, climate damages should affect the drivers of economic growth and not only the level of GDP. The rationale is that climate will provoke direct and indirect damages which will reduce the level of expected production. This is modeled through an energy losses function which affects the final energy consumption available for production after climate change impacts. Second, this energy damage function is calibrated by applying an inductive method to assure consistency with climate change impact assessment. Each user can calibrate this function through the interpretation of dangerous or catastrophic climate change levels. An example of energy losses damage function is shown in the slide. At current CO2 concentrations, damages are negligible, while at high concentrations, damages will be catastrophic. A logistic function is used in order to represent the nonlinearity between climate change and the related impacts. The parameters A and B can be selected by the user in the inputs Excel file. The parameter A indicates for which level of CO2 concentrations 50% energy losses are expected to occur, while B controls the steepness of the curve. To finish this session, let's see what the implications of such a modeling for a business-as-usual scenario will be up to 2100, assuming no other constraints such as energy availability. We will focus on the evolution of two outputs, global GDP on the left and global average temperature change on the right. The gray curves represent the projections without considering climate change damages. As expected, production increases exponentially, and so does the temperature change, which reaches similar levels to other business-as-usual scenarios in the literature. Let's see now how the introduction of the energy losses functions affects the results. Assuming a dangerous warming level of 750 ppm and an intermediate steepness, the red curves are obtained. After 2050, climate change damages cause a global recession and expected GDP levels cannot be attained. These results are more consistent with climate change impact assessments in the sense that if current trends are maintained within a business-as-usual storyline, a severe crisis and even collapse of the system is more likely than to reach 4 or 5 degrees without affecting the socioeconomic dimension, as currently reflected by most models. Concluding, the three main takeaways of the topic number 5, focus on climate change, are the following. First, MEDEAS work incorporates a state-of-the-art sample climate emulator model to represent the climate dimension. Second, large uncertainties exist in the estimation of climate change damages, which nevertheless have potential catastrophic consequences for humans and the biosphere. Third, a novel, simple, transparent, and consistent with climate impact assessment methodology has been developed for the integration of climate damages in the model. You will find the supporting material in the following website and the related bibliography and figure credits in this slide. The next and last video of this course will focus on the simulation of scenarios and policies with the MEDEAS world model. Thank you very much for your attention.